Okay, thank you, Johannes. Thanks to the organizers to give me this opportunity to present here some of the work that we do. And so I'll try to keep it relatively light after lunch and just show you a lot of pretty colorful pictures. One sec, this one is not. I'm going to use this one. Neither. This one doesn't have an on button, right? Should be just on. Perfect. Good. So when I talk about exotonic nanomaterials, this is one of the, let's say, key examples that we can give that kind of illustrates the power that this material science kind of approach to light management gives us. And what we're looking at here are solutions of semiconductor nanocrystals where the only thing that we are changing is the size of the crystal, and this gives us access to all these different colors of emission. And in this talk I will explain a couple of these strategies that we have to basically, from the perspective of the synthesis of these nanocrystals, how we can use that to control how these materials interact with light, and how we can use that for device applications. But before I start, I just want to kind of briefly go into the general excited state properties of semiconductors, and we can kind of look at the two extremes. So on the one hand, we have bulk semiconductors. So semiconductors have large dielectric constants, weak localization, and the so-called exciton binding energy is typically much smaller than room temperature. On the other hand, we have molecular systems, which are the, let's say, the tiniest extreme of a semiconductor system, where we have small dielectric constants, strong localization of charges, and this leads to an exciton binding energy that is much larger than room temperature. So what does this mean? This means that if we excite an electron from, let's say, the ground state to the first excited state using light, in a bulk semiconductor, this will typically result into free charges. So your electron and your hole are free to move around. On the other hand, in molecular systems, because of this strong localization, small dielectric constant, we have a lot of interaction between the electron and the hole, and this leads to a binding energy between, so the Coulomb energy between these electrons and holes, to create quasi-particles that we refer to as excitons. And these excitons are basically just packages of excited state energy that live inside these molecules, and they live for a certain amount of time, and they can decay through various channels. What is important is that this is basically like the two ends of the spectrum, but if we go halfway in between, roughly, then we have these systems where what we can do is take the bulk semiconductor, scale it down, and because of the restrictions in size, we force the electrons and the holes to be close together. So this means that now in a semiconductor system, we still have exciton binding energies that are relevant at room temperature, meaning we can engineer these semiconductors in such a way that we can create these excitons. Now the size that we're talking about is typically in the order of 2 to 10 nanometers, and these particles are synthesized with synthetic methods, and I'll get to that in a minute. And what's interesting about these systems is that you can process them from solution into films, but of course the moment that you go to these films, all kinds of interactions between these particles become important. This is going to be the second part of my talk. So let's first dig a little bit into this color tunability that I mentioned at the first slide. So the size tunability. So if we talk about these excited state properties of the nanoscale semiconductors, then basically when we create the excitation, we have the electron and the hole. The electron in the hole, depending on the dielectric constant of the semiconductor that we are using, has a specific length at which they kind of feel comfortable, which is the exciton Bohr radius. The moment that we reduce the size of our particle to a size that is smaller than this exciton Bohr radius, we are forcing the electron and the hole to be closer together, and this creates this additional energy that we need to pay to create the excitation. So as we are going from larger particles to smaller particles, we are increasing the energy required to excite an electron. We also increase the energy that is released when the exciton is recombining. So this leads to both tunable absorptive and tunable emissive properties of the material itself. So this is the spatial confinement, but when I'm drawing these positive and negative charges of the holes and the electrons, then we also need to realize that, of course, that leads to, let's say, a dipolar effect and electric field lines that are being generated. So there is a secondary effect. So this is the quantum confinement effect. There's a secondary effect, which is dielectric confinement. If we draw these field lines in a large bulk material, then basically these field lines will see the same dielectric constant all throughout. Whereas in a tiny particle, these electric field lines are now extending beyond the size of the particle. So we need to be careful to, when we are describing these kind of excitons, that we need to take into account, let's say, the effective refractive index or the effective dielectric constant of the environment, both taking into account the tiny semiconductor nanoparticle, but also perhaps the more organic environment. So these two effects together lead to this kind of tunability, very sensitive tunability of the system. So if we then have this very intimate relationship between size and the optical properties, this means that when we are making these materials, we need to be very careful to maintain a very low size polydispersity. Because, of course, any size polydispersity that you have, so any variation in the size of your total ensemble, is going to lead to a broadening of any spectral features that you have. So I'll come back to that in a little bit when we talk about the synthesis of these materials. Then we can talk about the dimensionality, because so the typical textbook example is just like the zero-dimensional particle in a box. But of course, if you can also control the shape of these materials, then you can create one-dimensional nanowires or two-dimensional nanoplatelets. And indeed, in recent years, thanks to a lot of these synthetic advances, through these chemical synthesis means we can control these kind of things and create what we call quantum dots, quantum rods, or quantum wells, or nanoplatelets. There's many different names for these kind of systems. Now, in view of the time, I'm not going to be talking about the entire family of let's say, these kind of materials. I'm just going to focus on the quantum dots, where there's already a lot of interesting things to see. So when we zoom in on one of these quantum dots, when we synthesize them in solution, this is kind of what they schematically look like. So we have this core, which is our size-tunable nanoparticle. So this gives us this access to the different colors of the material. And they are typically epitaxially coated with a shell of a material with a slightly larger band gap. And this is to basically protect the exciton that is residing in the core. So what this looks like is your typical core shell type 1 band alignment, where your exciton, so your electron and your whole wave function, is in the core, and this steep shell band edge is giving you control over the confinement. This is your typical system, but you can play with this. So you can choose your combination of core and shell such that maybe you don't have a type 1 alignment, but you have a type 2 alignment. So now your electron is confined into the core, but your hole is delocalized in the shell. And this gives you access to basically start spatially separating your electron and your whole wave function, which has implications for the dynamics of the system. If they are spatially separated, then basically the overlap that is reduced results in much longer lifetimes of the excitonic state. It's another tuning knob that we have. You can have very different combinations as well. You can have quasi type 2, where the hole is still inside the core, but it can leak to the outside. So there's many different variations that you have here. So let me see. Yeah. So talking a little bit. I'm not going to talk a lot about the chemistry because this is a physics conference. But I think it's interesting to see how this goes. So this is the kind of specialist person that is doing this. It requires a lot of practice. This is real time. So this is not sped up. So this person is basically, so this flask here is at roughly 200 degrees Celsius, and they use the syringe with the precursors, jam it in there, and inject it as fast as possible. This comes back to this size polydispersity. You need to create all the nuclei instantaneously, such that all of them start growing at the same time. So you can imagine. So this is a relatively small scale synthesis. In the commercialized systems, they're talking about 5 or like kilogram scale synthesis. So then it's basically an automated gun, basically, that is injecting the precursors in that solution. So this has been developed. So the Bowendi lab at MIT was one of the basically the pioneer of this technique, the hot injection synthesis. And this has been optimized and perfected over the past 15 years or so, such that now we have extreme control over the size and the quality of these materials. Some of the general advantages of any solution processable material, of course, just to summarize, you can process them at low temperatures, which means that you have flexible, you have the opportunity to make flexible substrates with these materials to make any optoelectronic device that you want. You can use for that any printing, spray painting, or inkjet printing techniques. So this is just a little bit of the sales pitch for the engineers. Now this until a few years ago, working in this field, it's of course always nice that you see all these very nice bright materials. But what is even nicer is that nowadays you can go to your local media markt, and actually the latest generation of TV screens, they are not anymore made with organic light emitting devices, but they are actually made of this QLED technology. Basically what they're doing here is they're substituting the organic light emitters, which have a relatively broad emission spectrum, for quantum dot emitters, which is a much sharper emission spectrum. And what you can do then, if you have these sharp emission features of blue, green, and red, is that you can create colors that have much higher purity than in the case of organic. So you can basically, in these kind of CIE diagrams, stretch out your color gamut, it's called, and create redder reds, greener greens, and bluer blues. So much for the sales pitch. But it's important to realize that all these systems that are now on the market, not just from Samsung, but also Philips and Sony are doing these are quantum dots embedded in polymer matrices. So we should still treat them as individual quantum dots. One of the questions that I'm interested in, that I got interested in a couple of years ago, I mean, if you want to really process these into electronic devices, how do you translate the properties of these very high quality nanoparticles, so these building blocks, into densely packed functional assemblies? There's a lot of studies that have been done to the electronic properties of these nanocrystal films, but the excitonic properties. So how does the exciton as a quasi-particle, as a package of excited state energy, how does it behave in these kind of assemblies? What becomes very relevant if we talk about the excitonic dynamics in these assemblies is basically the dipole-dipole coupling that you have between, again, like these electric field lines that are emitted by this particle and how it couples to its neighbors. So basically, it's a very conventional problem of how to describe energy transfer between donors and acceptors. And if we look at the general theory that you use for that, then from let's say all the biology studies, we look at first resonance energy transfer. And the way this is typically described for organic molecules, for instance, that can also transfer their energy through dipole-dipole coupling, is that there is a specific distance of interaction that this exciton has within a certain environment, and this depends on the refractive index mainly, but it also depends, for instance, on the spectral overlap between the donor and the acceptor. So this is the relevant distance, and if we then need to define a rate of transfer between a donor and an acceptor, then we take this interaction distance and we compare it to the actual distance between the donor and the acceptor, and this gives us a very distinct drop-off of the energy transfer interaction. Now this is basically what is describing a single step from a donor to an acceptor in such a film. But what I was specifically interested in at the time is the exciton diffusion. So basically what happens if your exciton can take multiple steps and really starts probing the space around it, perhaps using that to harvest the energy. Then we can just write naively a diffusion coefficient, and the exciton diffusion length is then a function of both the time that it lives, so how far it can travel within the time that it lives. So this is basically the theory, and one of the questions from a materials design perspective that we wanted to ask ourselves then is basically, can we control this through material design? Can we design the material such to either promote or inhibit exciton diffusion? And the easiest parameter that we found is basically like, can we control the distance between particles and just see how that affects whatever we have? So we designed a set of materials, like through synthesis, you control that you have short ligands on the outside, a thin shell, a long ligand and a thin shell, and a long ligand and a thick shell. You characterize all the optical properties to make sure that they're more or less comparable. And you verify the actual distance experimentally, so not just by estimating it, through TEM analysis. You have a nice set of materials in which distance is the primary difference between them. But of course, can we control the diffusion length is just one part of the question, because the actual question that we needed to answer is how can you measure the diffusion length? Because the diffusion lengths in these materials, if you just kind of plug in some numbers in all these equations, they're not going to be terribly long. So we're talking about tens of nanometers of diffusion length, and this is not accessible through your conventional microscopy. So at the time, I was working with a bunch of colleagues there. This was at MIT. And my colleague, Gleb Axelrod, he came up with a very clever idea. So what we did was to take a excitation laser, create a diffraction-limited excitation spot, and project the fluorescence that comes off of this spot highly magnified onto a lifetime detector. And this detector area is much smaller than the actual laser spot. And what this allows you, so now the detector is giving you access to the time axis, whereas the motorized movement is giving you access to the spatial dimension. So this gives you access to a kind of mapping technique where you can follow the diffusion from this diffraction-limited excitation spot outward into the film. So here, this is basically the kind of map that you get from such a measurement. And if you look very carefully, so this is time is 0, where we just created the spot. So this is the diffraction-limited profile. And as time goes by, it's broadening ever so slightly. And this gives you access to actually extract the speed of diffusion in this film. So we do this for our three systems, and we plot as a function of time this change in the variance. So how much broader does it get with time? And what we observed, so this goes a little bit into the details of how energy transfer is affected by energetic disorder and those kind of things. What you would expect naively for just a random walk is normal diffusion, so it just diffuses out at a constant rate. Something that we observed, first of all, is that indeed with the increasing distance we see the diffusivity going down, so this is what we expected. What was a little bit less expected or more dramatic than what we expected is that it slows down as time goes by, and this is a clear indication of energetic disorder. So if you have high energy sites and lower energy sites in your system, in the beginning you probe all of them, but as time goes by you are populating more and more of the low energy sites, which have more difficulty of giving off their exciton to the next part. So from this, of course, this is just the, so this is basically the diffusivity as a function of time, so it's slowing down as a function of time for all three of them. And this does not tell you yet how far the exciton actually travels, so you can take the lifetime of the system and this time-dependent diffusivity and plug this in. And this gives you a bunch of numbers. I mean, this is not terribly important right now, but it's nice to see that the diffusion length is increasing as we decrease the spacing. But what I think is much more important here is that through this kind of understanding of how these material systems work in terms of the distance scaling, you can now start designing for your specific application. So if you want to harvest your energy, you want to promote diffusion, whereas if you want to create a light-emitting device, then the exciton that you've created, you like it to stay where it is because the only thing it needs to do is decay. Whereas if it starts diffusing, the only thing that can happen is that it dies through some quenching mechanism. Now for the second part of this talk, I want to kind of highlight a different strategy, that's more recent work, that is, can we use the ensemble itself to create functionalities. Let me just explain this. So we have these TV screens, right? And people are also making LEDs out of these quantum dots. And the interesting thing is that these quantum dots, thanks to all this passivation and everything, they have quantum yields that are close to 1, meaning every photon that you use to excite them gives 1 photon out. This is really thanks to the advances in the synthesis. So, and actually these LEDs that they are making, they have internal quantum efficiencies of close to 100%. That means that basically for every electron that you're injecting, you get a photon generated. But the external quantum efficiencies are quite low. What does that mean? So you are very efficient at generating light inside your device, but to get it out is a different question. Yeah? So what happens typically is that you generate this light inside this film, which has a relatively high refractive index of around 1.8, and only light that goes out in certain perpendicular directions is able to escape, but a lot of the light is actually trapped into waveguide modes. So typically when you look at one of these LEDs without any light management system, the edges will be what is extremely bright because the trapping efficiency is actually in the order of 80%, yeah? Which is explaining this external quantum efficiency of only 20. So this is a very old problem. It's just Snell's law. There's nothing new about this, and this is also something that people have seen in the past, of course, for organic light emitting diodes or solid state light emitting diodes. But one of the real questions from the quantum dot perspective is you have this quantum dot, this building block, which has this extremely high quantum yield. How can we now maintain that really high quantum yield as a functional device? So can we start controlling how light is actually coupled from this quantum dot into the far field? And there's a lot of work in this direction, like coupling quantum dots to photonic structures. So this early work where they place quantum dots in solution inside a photonic crystal, you can control the emission dynamics of these systems very nicely. Cavities, of course, have been used to create optical feedback even in these systems, again enhancing the optical properties from such a perspective. Yagi-Uda antennas to directionally couple the light out of these quantum dots, or plasmonics. There's also plasmonic cavities to really change the spectral shape and the dynamics and the directionality. So there's a lot of strategies available to take your quantum dot, couple it to a external structure, and control the directionality of outcoupling and those kind of things. We wanted to ask a more simple question and ask ourselves whether or not we could structure the ensemble of the quantum dots itself to create the same kind of control over directionality. So the way I like to present this is that now you have this nanoscale semiconductor quantum dot that we can tune the optical properties. But at the same time, if we combine that with a wavelength scale structured ensemble, we get the advantage of additional tunability by having these access to photonic modes. So coming back to the original problem of 2 slides before of this waveguide moding, I'm drawing here a grading type structure, and this is not coincidental because, of course, in organic light emitting diodes or solid state, it is exactly these kind of grading structures that give you this kind of Bragg scattering that allows you to couple light out despite the difference in the refractive index, because the grading is giving you this additional momentum. So for a specific color of light, you can change the pitch to get a specific direction of outcoupling. So this is just creating constructive interference. So this was kind of like on paper the idea, but then the question becomes, how do you actually create these kind of structures? The available techniques to kind of take these nanoparticle ensembles and create some kind of structure in there, you have the printing techniques, but they don't have a very high definition in the vertical direction. Also, the resolution is relatively limited. Same thing counts for microcontact printing using PDMS type printing. And lithography techniques are generally just kind of cumbersome. So this was kind of our starting point, but at the same time, we were working on some plasmonic patterning. So this is relatively simple compared to the quantum dots. So patterning plasmonic substrates is just your typical lithography techniques, but there's one technique. It's called template stripping, and this is very, very powerful if you're working on plasmonics. Definitely, if you didn't know this paper yet, definitely check out this paper because it's very, very flexible and very, very nice to create very high quality structures. So the way this works is you take a silicon wafer and you just pattern it with your standard lithography technique. Deposit your silver on top. At the back of the silver, you put epoxy and a glass slide. So you just basically glue a glass slide at the back. And then you take a razor blade and you clip off the silver from the original template. And the advantage of this structure as compared to that structure is that this structure has the smoothness, the flatness of the silicon. And this is essential in plasmonics if you want to avoid any scattering. So this was a technique that we were using extensively in the lab, and just as a kind of like a Friday afternoon experiment, we asked ourselves the question whether or not we could do the same thing with quantum dots. So instead of depositing silver in our evaporator, just put a droplet of quantum dots on there and try to see if you can clip it off. This indeed works, but I have to say that there was one essential step necessary for the quantum dots as opposed to the silver, and that's that you have to make sure that your silicon template is extremely non-sticky. Yeah? So you need to make a self-assembled monolayer on there that has very low surface energy, and if you do that, then you make sure that in this step, the razor blade clipping step, that your quantum dot silicon interface is the one that gets clipped and not that it breaks somewhere in the middle of your quantum dot film, which of course is kind of like a undesired idea. So this works very well, and after a little bit of optimization, here you see a couple of examples. So these are the templates. You cannot really see the patterns here. You can kind of see them here. So this also shows the color tunability, of course, of these quantum dots. You can red, green, and blue. And these are the stripped films that now have these patterns transferred into the quantum dot film, and the round shape is just where you've let the glue kind of flow out before it started to harden. So this is fluorescence photograph basically. What we can do as well is then take another razor blade step and kind of peel off the epoxy together with the quantum dots, so we can make flexible structures, which is just interesting and makes nice pictures as well. But what is more important, I think, is if we start zooming in, because what you see here already is that these structures that we have here are now extremely bright, and this is already an indication of this enhanced outcoupling. So this is an SEM image zoomed in on one of those gradings. So what you see here is there's no scale bar here, but the particles that you see are around 10 nanometers because these are semiconductor nanoparticles, and this structure is about 400 nanometer periodicity. So this is giving you this idea of the let's say hierarchical structuring of the material, and also showing you how high quality this is. There's a few defects, but really not that much. So we can do linear gradings. We can also do circular gradings. The advantage of a circular grading is that if we think back on this Bragg scattering condition, then we are now fulfilling this condition in all radial dimensions, which means that instead of just controlling light on one dimension, you can potentially create a beam of light that is scattering directional in all dimensions. So this is changes in the pitch of this bullseye thing, and here you see that for the 400 nanometer pitch you get this very bright outcoupling. So to check this kind of directionality, we perform Fourier Microscopy. So what this does is a very simple technique that sounds more complicated than what it is. K-space imaging or Fourier imaging is nothing else than just looking at the backside of your objective, and the backside of your objective, because of the way an objective works, light that is emitted under a high angle comes out on the side of the objective, whereas light that is emitted perpendicular to the surface comes out at the center of the objective. So basically the backside of your objective is always just a map of whatever angles you've probed in your system. So you can do this and you can create these maps. And indeed, for the 400 nanometer case, we get this high intensity at the center, meaning that this is really a beam of fluorescence that is now coming off of the sample. And again, so what is important, I think, to remember is that this is nothing else than just taking the quantum dot film and creating a little bit of structure in the ensemble. You're promoting the outcoupling of light very nicely. So for other pitches, you are emitting at a higher angle, so this creates this kind of donut-shaped beams. So if you quantify this, then basically you get a twofold increase in total brightness just by increasing or just by introducing this this structure. Sixfold for small view angles. So just if you are interested in just collecting the light of the beam, you get something like that. Okay, so this is a strategy. This is a very basic demonstration of just what you can do with this. This is to promote the outcoupling. We can do other things because any pattern that you can create in your silicon, you can transfer to your quantum dots. So for instance, you can create pyramid-shaped protrusions. So this is a 5 micrometer base pyramid consisting of about 250,000 quantum dots. These kind of structures may be interesting to create like more omnidirectional outscattering or also more broadband performance of the same type of strategies that we've shown here. Just in the last couple of minutes, I want to highlight one other thing. So because here we are trying to promote light to come out, but we can also use your photonic waveguide kind of strategies to trap light on your chip. Quantum dots are very good gain materials. So if you create ring resonators, this can give you a very nice laser cavity. So ring resonator cavity for lasing. So you can do your nice COMSOL simulation, very simple, to check whether or not the geometry is good for a waveguided mode. We engineer our quantum dots a little bit because in a waveguide what you don't want is a lot of reabsorption. So what you can do actually in quantum dots is create very thick shells which effectively separate the absorption from the emission in your quantum dot, which means that the emission can travel while the absorption is relatively low. Another example of how you can use the quantum dot structure to engineer whatever property you're interested in. And this is one of those ring resonators. An SEM image is about 10 micron in diameter. And if we focus down our laser on one side, we can very nicely see that it lights up. So this is just a little bit of scattering that is coming off of the quantum dot waveguide. But you see that it's basically allowing the light to travel very efficiently. We can look at the scattering a little bit in the here. Just take the spectrum, and we can see these very nice interference peaks with quality factors up to 2500, which for quantum dot resonators is one of the highest reported. And of course, this is proportional to the radius of the system. What we're really interested in is lasing. So now instead of focusing the laser down on one edge, we basically just carpet illuminate the ring laser. And indeed, with lasing thresholds really quite low of 20 microjoule per square centimeter. So again, this is just a number, but just to give you an idea, the record right now, after we did this, is now at 5 microjoule per square centimeter. But this is really one of the lowest reported numbers. So, and the nice thing here is that we are not requiring any external cavity, but we're just structuring the film itself to create this feedback for the light. With that, I would like to conclude. I want to thank my team members. This is my group. We are located here in the Autónoma, Madrid. This is here in the mountains, actually. Eva is the one that has done a lot of the work in the latter part that I've presented. She's the one that's still located at ETH, where my group was before. She's finishing now. Michael, Alvaro, and Michel are here. So if you have any other questions, you can of course approach me, but you can also ask them. And I would also like to thank my collaborators at MIT and ETH and my funding agencies. If you have any questions.